Hello friends, welcome to today's session. So find the oxidation state of the underlying species. So the oxidation state of carbon is to be determined, that is X plus number of oxygen atoms are 2. The oxidation state of oxygen is supposed to be minus 2. Algebraic sum of all the elements, as long as charge is not there on the entire molecule, if it is neutral, the algebraic sum of oxidation state is 0. So X came out to be plus 4. Similarly, if I would go for this, oxidation state of nitrogen is to be found taken as X. Number of hydrogen atoms are 2, for which the oxidation state is assumed to be plus 1. Because it's an anion, the charge on anion, the sum of algebraic sum of oxidation state is equal to the charge on the ion, that is minus 1. So the X comes out to be minus 3. So what exactly do we mean by these oxidation state is the point. Let's go into the details. Myself, Gurpreet Singh, I am going to take up this topic of oxidation state in detail. So why I'm placing this video, because some time back I have discussed the topic of N factor. I just have made at that point of time 6 parts pertaining to N factor of acid base, redox reaction, oxidizing agent, reducing agent. So it is in length. There I have used the term oxidation state time and again. So people are asking me to elaborate it in more detail. What exactly do we mean by oxidation state? So before going into the depth of the, otherwise it hardly took me 2 minutes to explain what exactly do we mean by oxidation state. But if we dig deep into the topic, what exactly do we mean by oxidation state, for which we need to understand few things before I go into the depth. First is the from the chemical bonding or from the periodic table, electronegativity. Electronegativity of an element is its tendency to withdraw shared pair of electron towards itself in a given covalent bond. Say for example, if I write HCl, we used to say chlorine is having 7 electron, valence electron, and 1 is of the hydrogen. So chlorine being more electronegative than the hydrogen, this shared pair of electron is a little displaced towards the chlorine. As a consequence, chlorine would get a delta negative and this would get a delta positive charge. So this tendency of chlorine to withdraw shared pair of electron towards itself would be said as to be its electronegativity. Or other way around, I can say electronegativity of chlorine is more than that of hydrogen, for which you need to remember a bit of on the Pauling scale what is the electronegativity values of different elements. So we can see here very categorically that fluorine is the most electronegative, for which the Pauling value is 4. Pauling scale is a scale on which the electronegativity is being found. So majorly we would be concentrating on the hydrogen, for which it is 2.1, and these elements which I am marking it here, you can see all of these are having oxidation state greater than that of hydrogen. We would be requiring this time and again during this discussion. And rest of the things you can the values, if you could learn it would always be a great. So simply I am saying carbon, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and here you have sulfur and phosphorus. These would have electronegativity greater than that of hydrogen. This is always you have to remember. So this point you always have to remember. Another thing, when before I go into the discussion in detail, there are two types of bond, breakage or cleavage. When you want to break any bond, there are two ways to do it. One is homolytic bond cleavage. Homolytic bond cleavage you would find if in case this is a single covalent bond. If I would break it from the center such that the bond breaks like this, as a consequence you would get Cl dot and Cl cross. Dot and cross I am just marking it from the standpoint of view that's so that you could feel the two electrons, which electron belongs to the which atom. So homolytic bond cleavage is a cleavage where you would break the bond from the center such that you would end up getting free radical. Free radicals are the neutral species where the octet of element is incomplete but it is neutral. So homolytic bond cleavage we generally would see where the electronegativity difference is almost zero. and that thing we would see when the two similar atoms are joined by some bond. And as regard to the heterolytic cleavage simply would mean, as I said, chlorine is more electronegative than hydrogen. So heterolytic cleavage is a cleavage where the bond happen to break, not from the center, because the more electronegative element would withdraw the shared pair of electron towards itself. As a consequence, the bond happen to break it like this, because this particular electron is of the hydrogen which gone to the chlorine, and chlorine now would carry extra electron of that of hydrogen, so it would get a negative charge and this would get a positive charge. So in a way, heterolytic cleavage would lead to the formation of charged species, and charged species definitely would be cation and anion. So this is said as cation and this is anion. This topic indeed is again a quite lengthy one. Here I am just minimum amount of things which I would require to explain the oxidation state that I'm taking up. So I think I just have taken two things. One is electronegativity and second is the order of electronegativity. If you can remember the values well, otherwise you just would remember these elements would be having a more electronegativity as compared to hydrogen. And lastly, and also along the period, if I move, electronegativity increases, and down the group if I go, electronegativity decreases, because if I move down below the hydrogen, the electronegativity would be less, and beryllium is having electronegativity 1.5, and as we move down, all the elements below lithium and beryllium would have electronegativity lesser than that of hydrogen. Now, as a matter of fact, if you would see into the different books, this is the simple rule of the games. There are 4-5 rules on which everything get played down, but when you dig deep into the topic, it is very, very interesting to explain. Now, all these 5 points I am going to explain. First, let us define what do we actually mean by oxidation. Now, this oxidation number or oxidation state, I would prefer to speak more on, I would be using the name as oxidation state. Now, what exactly do I mean by oxidation state? Oxidation state is the actual or apparent charge. Now the point here is there are two terms. Actual charge means when the species is having actually the negative or positive charge on it, and apparent charge means, apparent word in itself suggests what? Apparent means something which is supposedly be there but actually is not there. So we are presuming that this species if would get this particular charge, but that charge in a given molecule is actually not there. Let me explain what I am trying to say here. So it is the actual or apparent charge a given atom would have in a given chemical species when atoms around it are theoretically removed. Make it a point, what I wrote here is theoretically removed. Now what does it mean? Now let us dig deep into it and try to understand what do we mean by it. Just like the point number 1 is that if you talk of oxidation state of any element in its elemental or native or pure form, we assume to take that oxidation state as to be 0. The oxidation state of an element in native or pure form is assumed to be 0. Now what does it mean? Now along with I am going to explain the definition as well. Now I am explaining the definition and that point as well. Now if I would say hydrogen molecule and I am interested to find the oxidation state of hydrogen, so what is the viewpoint? When I write hydrogen like this, it is having a single covalent bond. One electron is of this hydrogen and another electron is of this hydrogen. Now the point here is, if I just would want to find out the oxidation state of this element. Now what the definition says, it says that because it's a neutral molecule, it did not have any charge. So what we will be saying, the apparent charge which this hydrogen atom would receive when atoms around it are theoretically removed. Now this is the hydrogen around which we wanted to find the oxidation state, and it would get a oxidation state only if the atoms around it are theoretically removed. Now the point here is it is attached to hydrogen itself. So the theoretical removal could be homolytic or heterolytic, because both are having the same electronegativity, the bond get broken from here. Now when the bond get broken from here, the charge which this oxygen, the apparent charge which this oxygen, this hydrogen would receive would be 0, because it did not get any charge. On breaking this bond, this electron had been of, this particular electron had been of hydrogen number 1, and it goes to the hydrogen. So the oxidation state this particular element would get is 0. And same is the case if you wanted to find the oxidation state of hydrogen here, and you have to theoretically remove atoms around it, and theoretical removal would be with the homolytic cleavage, because both are electronegativity difference is 0. So this would also get a 0. So this is the point which you always have to remember, that the oxidation state is the apparent charge which an atom receives when the atoms around it are theoretically removed. Say for example, if I would go for fluorine, generally in the books, or we also tell you that the oxidation state of any element in its native state is 0. Why is it 0? It is 0 because of the fact when you actually would make its bond and would like to do the bond cleavages, theoretical bond cleavage, because as per the definition, if I want to find out the oxidation state of this fluorine, I have to remove atoms around it. And in doing so, because fluorine is having 7 electrons, 7 of this and 7 of this, their octet got completed, so it's a single covalent bond. So if I would break it from the center, what charge did this fluorine would get? It would not get any charge. The apparent charge on it would be 0, because it did not get any charge. Same is the case for this one. So that is why we used to say that whenever element is in native state, just like in this oxygen is double covalently bonded, and if you want to find out the oxidation state of this oxygen, I am repeating the same thing once again, I have to break the bond from here, and in totality the number of electrons around is 6. So the apparent charge, let's say this oxygen have received is 0, because the 2 electron cross electron are of this oxygen only, and it happens to get with that particular oxygen on theoretically homolytically cleaving it. Similarly for nitrogen it is 0, because N triple bond N, and you have 3 electrons on this side, 3 electrons on this side, and if you theoretically would remove, this would get 0, this would also get 0. So the point here is, when 2 atoms are joined by double, triple or single bond, and the 2 elements are same, the apparent charge which you would get on theoretical removal on both that atoms would be 0 and 0. Now coming on to the metals, if you have a sodium, pure piece of sodium metal, so it would not get any charge, it would be 0. For that also calcium is also 0, iron is also 0, because if sodium is in the crystal lattice with the other sodium atom and so on, the apparent charge on it is 0. Okay, so now going on to the heterolytic bond cleavage or heterolytic molecules, like let's say going for the HCl, we wanted to find the oxidation state of this hydrogen and chlorine. So what I would do, I would make the bonding. The bonding is this way. Now we know for sure that we wanted to find the oxidation state of this hydrogen, and we know for sure that hydrogen is less electronegative than chlorine. The electronegativity and of chlorine and hydrogen, chlorine is more electronegative. So if I just would want to remove around hydrogen who is present, chlorine with the single covalent bond, and I want to remove it theoretically, here the bond cleavage would be heterolytic. Why is it heterolytic? Because chlorine is more electronegative. Now here the definition actually signifies many things. The apparent charge, I am writing the word here apparent. Apparent means which supposedly be there but actually is not there. In totality in HCl there is no charge, but on heterolytic cleavage, if it had broken it that way, this would get 1 positive charge, because this electron, this particular electron which was of hydrogen now is with the chlorine. And now if I want to find out the oxidation state of chlorine, so this would be -1. I think I made my point clear. So why it got -1? Because the chlorine has theoretically we have removed one, or chlorine has taken along with one electron of hydrogen during the heterolytic cleavage. As simple as that. Now moving ahead, if I would want to find out the oxidation state of hydrogen, oxygen and hydrogen in water, so I need to make the structure. The only thing is, when you dig deep into the oxidation state of an element, if you literally want to understand the oxidation state, otherwise with the formula, whatever oxidation number or state we would get, it's okay. But the point here is, if you want to dig deep, you have to have a little understanding of bonding. So the point here is, and for that also you can see some of the videos already uploaded in regard to the bonding, especially in the organic series. So there I have explained all these Lewis dot structure in detail. So this hydrogen and these cross electrons are of oxygen is having 6 valence electron, and this is the hydrogen. Now what we will be doing, if I want to find out the oxidation state of this hydrogen, I have to, because again the electronegativity of oxygen is greater than hydrogen, so the bond would get broken from here. So here what you are able to see, this would get +1, and this electron which was of hydrogen now went with the oxygen, so this oxygen would receive apparent charge as -1. Similarly, if I would break it from here also, this would get +1 and this would get -1. So what beautiful thing we are generating here. The beauty of the thing is that oxidation state is coming from every bond. So this is +1, and for this -1 becomes -2, and this is +1. So that is why we used to say some algebraic sum of oxidation state of all the elements in a neutral molecule happens to be 0. It makes sense. It is not to be crammed. It is logical that if you just would find the oxidation state of all the elements, theoretically the algebraic sum of all the elements, oxidation state of all the elements would come out to be 0. Now coming on to the further. Now if I would take the case of hydrogen peroxide, here the bonding is this way. And don't be disheartened if you don't know the bonding. For that you could see that videos where I have explained the how to make the Lewis dot structures. Now here the bonding is somewhat like this: cross, 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 and this is dot, dot, dot. I am writing cross and dot so that we can easily detect which electron belongs to which element, because it is mutually shared. Now the point here is, you have to break this bond if you want to find the oxidation state of hydrogen. So it comes out to be +1, being oxygen more electronegative. This is -1 because this electron of hydrogen is now with the oxygen. Similarly on this side also, this is +1, this is -1. Now the beauty of the thing is, now you have to be little vigilant about this bond which is in the center. Now if I just would want to find the oxidation state of this oxygen, as per the definition, you have to theoretically remove all the elements around oxygen. Here I have broken it with heterolytic cleavage. Here I shall be doing homolytic cleavage, because oxygen would not have any electronegativity difference. If you have to theoretically remove it, I will break it from the center. So here the apparent charge is coming out as 0 from this bond, and here it came out to be -1. So this is very, very important to understand here. So the oxygen tend to get, if I would write the oxidation states now, this is +1, and here it is -1 from this bond. From this bond it comes out to be 0. So in actual this comes out to be -1, and same is for this, and this is +1. And if I do the algebraic sum of all these, it happens to come out to be 0. If you just would do the algebraic sum of all these elements, it happens to come out to be 0. So here a point of caution is there. The point of caution is, generally we will say, generally we would say that when you wanted to find the oxidation state of an element, here there is a point of interest and interesting point, that we happen to get something like this. Here the oxidation state happens to come out to be, for this is +1, for this total is -1, -1, +1. So make it a point. Generally we will say the oxygen generally would get -2 oxidation state whenever it is attached to less electronegative element. Generally it is that way. But if there is a proxy linkage, if the oxygen is joined with each other, then on breaking, here you would get apparent charge 0, here you would get apparent charge 0. And if it is attached to some electronegative element like hydrogen here, or less electronegative element like hydrogen, so from here it would get -1, here it would get -1. This is called as proxy linkage. Or in other word around, if I just would mark it here, if somebody would ask you O22 negative, you wanted to find the oxidation state of this oxygen. So basically this is dot, this is cross, this is dot, this is cross, and you have taken out 2H. This H went out, this H gone out as H positive. So here this cross now would have this cross which was of hydrogen, this cross which was of hydrogen now would appear as a complete actual charge. This would appear as O negative, complete negative charge, because now we would say, because the two hydrogen went out as H positive, leaving behind their 1 electron. So that is why now this is actual charge. This is actual charge, and from this bond it is 0. So the oxidation state happens to come out to be -1, -1. So, and if you go with the formula, what we used to say, 2x, oxidation state of oxygen we wanted to find out is -2, x comes out to be -1. Now similarly, if I go a little more in detail, just like in case of ammonia, if I would write the case of ammonia, ammonia has this structure 1, 2, 3, and these are the cross atoms of the hydrogen. And if you want to find out the oxidation state, so because again the electronegativity of nitrogen is greater than that of hydrogen, so here if I would break it from this position, so here you would get +1, here it would get -1. Similarly, you have to break it from here, +1, -1, break it from here, this is +1, this is -1. So in totality, on this nitrogen you happen to get -3 oxidation state, and for the hydrogen it is +1, +1, +1. And if you do the algebraic sum of all, plus 3 hydrogen atom of +1 versus 1 nitrogen of -3, algebraic sum happens to come out to be 0. As simple as that. Now similarly, if I would go for the from the ammonia, if I just would make one more here, just we have said ammonia, for which the system was this way. Now if in case I just would write that I have, these are the electrons of the nitrogen, cross, 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 and if I just would take this H positive out of the system in actual, then the species which I would receive here is something like this. This went out as H positive, it H came out giving its electron to the nitrogen itself. So dot and cross is there, this dot and cross is also there, this dot and cross is also there, and nitrogen is having one lone pair as well. So what we are able to see here is, now on this nitrogen from this side, this cross which was of hydrogen, let me mark it very categoric, this cross I am talking of, this cross is of hydrogen, now is with the nitrogen. So the actual charge on nitrogen is -1. And now if I would see into this particular bond, in this particular bond you have to write it this way only, that this is +1, this is -1. And similarly, if I would break it from here, this is +1, this is -1. Now if I would write the total oxidation state, on this hydrogen it is +1, plus on this nitrogen it is +1, plus, and if you would see here, in totality, what is the total charge? This is -1, this is -1, these are the apparent charges, and this is the actual charge, that is also -1. So the sum of apparent charges and actual charges is the oxidation state of this nitrogen. So that is -3, which is equal to, we used to say it like this when you have a anion given to you. Just like if I would write once again, NH2 negative, that is amide. If I go with the formula, x plus 2 into +1 equal to -1. So the answer comes out to be -3. So that do make a sense, that when you have a given species as a anion or a cation, the algebraic sum of oxidation state of all the elements happens to be equal to the charge on it. Why this charge we have taken equal to? Here it is getting a meaning, because then only the two terms would equate. This side would equate to this side. Although the nitrogen is carrying -3 and it is coming with the formula as well, -3, but here the point is, logically, when we say that the algebraic sum of oxidation state of all the elements in a given polyatomic anion or cation is equal to the charge, that why we have taken that charge is to explain that thing. So this is very, very important. Similarly, if I go further, like perchloric acid, here if you want to find out the oxidation state, we used to say for the chlorine it would be, so hydrogen we have taken as +1, generally it is in +1 oxidation state, plus X we want to find out. Oxygen mostly is in the -2 oxidation state, so there are 4 oxygen, -2 equal to 0, because it's a neutral species, so it comes out to be +7. Let us check this out. So perchloric acid has this sort of a structure. Now in this sort of a structure, if you want to find out the oxidation state of chlorine, say for example, so here these dot electrons, 7 valence electrons is of chlorine, and these cross electrons are of oxygen. So apparent charge which we will be getting, because again you have to understand here is oxygen is more electronegative than chlorine. So the bond breakage would happen if I pick each and every bond around it. So the breakage would come like this. It get broken from here. So it is +2. This is -2. Similarly, if I would break it from here, so it comes out to be +2, -2. Similarly, here also +2, -2. And in this particular bond, because it is a single bondality attached to the oxygen, so if I would break it from the here at this position, so the chlorine would receive oxidation state +1 and this would get -1. And the other oxygens which now, the only oxygen which we have left, for which I have to break the bond from here, because oxygen is more electron, -1 from here, +1 from here. So what oxidation state did we get? +1 for this, -2 for this, and although it has become little chaotic, +2, +2, +2 from these 3 bonds, +1 from this bond, so it comes out to be +7. And other 3 oxygen also would get a -2, -2, -2. So -2, -2, -2, and this is -2. So the total become -8, +7 for chlorine and +1 for hydrogen. Total is +8. So algebraic sum happens to come out to be 0. So here what we are able to understand, that oxidation state of most oxidation state in a covalently bonded species come from each bond, and that bond breakage has to be done very carefully. Hydrogen is generally bonded to more electronegative element. Generally hydrogen is either joined to, let's say I joined it with carbon, say for example, or hydrogen is joined with nitrogen, or hydrogen is joined with oxygen, or hydrogen is joined with some halogen. So wherever it is joined with a more electronegative element, it always would get +1 oxidation state. Why we are getting +1 oxidation state? Now you have a logical interpretation of that, because if I would break this bond theoretically, the apparent charge which this hydrogen would receive is +1. Whereas when hydrogen is in the ionic form, when it joins with the hydrogen, say for example, here it is Li positive, H negative. So here the lithium is in +1 oxidation state and hydrogen is in -1 oxidation state, because the fact is the lithium is alkali metal which is having lesser electronegativity than hydrogen. So hydrogen will take out the electron and would carry 1 negative charge. And similarly, if I would go further, and this way you can do as many problems as you can, I will play some other session also for the practice. Now coming on to the next part is ionic salt. For the ionic salt, whatever cation and anion carries the charge, that is the oxidation state. So sodium +1, chlorine -1. And similarly for this, if I would write X plus 3 into -1 equal to 0. So X comes out to be +3, because when it got broken, just like this get broken into Na positive Cl negative, Fe3 3 positive plus 3 Cl negative. So this also you always have to remember that in ionic crystal, the charge which you are receiving would be the oxidation state. Now here I do make a point here which is very very important to explain here. At times you would see, just like if I would write Na2SO4. Now if I would break this at times people get confused with. So this is sodium sulfate. Now this sodium and sulfate are in the ionic form, but this sulfate ion is, because it's a polyatomic anion, it is having a lot of covalent bonds. So the covalent bonds are like this. So now it is your discretion which way you want to see. If you want to see through the bonding aspect, now the oxidation state happens to come out to be, because these are the electrons of the sulfur and one cross electron is of oxygen. So if I would break it from the here, from this position, so because oxygen is more electronegative than sulfur, so if I do the bond cleavage from here, this would get a negative charge, apparent 1 negative, and this would get 1 positive, and the oxygen which is double bondedly joined, so this would receive, or let me show it to you once again. Okay, so this would get plus 2, this is going to get minus 2, this is plus 2, this is minus 2, and from this bond plus 1 minus 1. So this sulfur happens to get, if you would be able to see it, we are able to show you, this is plus 2, am I right? This is plus 2, this is plus 2, this is plus 1, and plus 1 and plus 2, so it comes out to be plus 6. So the sulfur here is carrying plus 6 oxidation state, oxygen is in minus 2, sodium is in plus 1. So this is again very very important to understand that in an ionic compound, a anion can be polyatomic, or cation can also be a polyatomic, like ammonium. If I would write it here once again for you, say for example ammonium sulfate. Here the cation is in the polyatomic form. So ammonium sulfate, this is ammonium sulfate. So here if I would draw the structure of ammonium ion, it would look like this one. This is the ammonium ion, and this carries 1 positive charge. Actually I missed the example here where I was discussing the amide. Along with that I wanted to discuss the ammonium. Anyhow, let us see here. So here nitrogen is having 3 electrons, and these electrons are of nitrogen, and these cross electrons are of hydrogen. Now since nitrogen is more electronegative than this, so this is plus 1, this is minus 1. From here also this is plus 1, this is minus 1. Oh, I wrote it reverse. This is minus 1, this is plus 1, this is minus plus 1, this is minus 1, and similarly from this bond also, this is from this bond also, this is plus 1, this is minus 1. So the oxidation state which we are able, because nitrogen is also carrying 1 positive charge, actual charge, so actual charge and minus 1 get nullified, so the total oxidation state happens to come out to be minus 3, and for all the hydrogen it come out to be plus 1, and algebraic sum of the oxidation state of all the elements happens to be equal to the charge, that is 1 positive. So what I said, 4 hydrogens in plus 1 oxidation state, plus minus 3 is of the nitrogen, and which has to be written equal to plus 1, that is the charge on the anion. So this happens to come out to be equal. Now coming on to the important part of the discussion, which in the video may go in length, but this is very very important. When the element for which you are wanting to find out the oxidation state, and the atoms of that element in that particular molecule are more than 1, just like in this case, you are interested to find the oxidation state of carbon. You are interested to find the oxidation state of carbon, but the number of atoms of carbon in this particular molecule is more than 1, then the oxidation state which you would get from the formula is a average oxidation state. When the element for which you are wanting to find out the oxidation state has more than 1 atoms, then we always would get average oxidation state from formula. It would not depict us the actual oxidation state. What does it mean? Now, if I would do 2x, for this I wanted to find the oxidation state, plus 6 into plus 1 plus minus 2 equal to 0. So this happens to come out to be, if I would find oxidation state happens to come out, so this is plus 4 and this comes out to be minus 2. So the oxidation state for the carbon in this particular compound happens to come out to be minus 2. Is it okay? Now, if I just would draw its structure, now this is very, very interesting. Now C2H6O. Now, if I would draw its structure, it may have this sort of a structure. This is again very, very interesting. This is alcohol. Now, if I just would see what are the oxidation states do I get here. Now, carbon is more electronegative. Carbon is more electronegative than hydrogen. So, for the first carbon atom, if I would show what are the oxidation state do I get, the bond get broken from here, plus 1, minus 1. Similarly, broken from here, hydrogen is less electronegative, so this is minus 1. Similarly, minus 1, plus 1. And from carbon-carbon bond, it happens to come out to be 0. So this is 0, this is 0. So the oxidation state which I received for this carbon happens to come out to be minus 3. And that for, let's see for the next one. So here what we are now writing, the oxidation state of this carbon crosses of hydrogen dot cross dot cross. And now if I would write the oxidation state once again, so this is plus 1, this is minus 1. Here this is minus 1 and plus 1 because hydrogen is more electronegative. But as a matter of fact, here it is 0, 0 because the bond would get broken homolytically. Now the important thing is that if I just would mark once again this particular bond would heterolytically cleave because oxygen is more electronegative than carbon. If I would write the electronegativity, so the bond would break it like this, minus 1, and this would receive plus 1. So that means this particular carbon is having oxidation state minus 1, plus 1, minus 1. So its total would become minus 1. So what is very interesting, that what we have said, if I wrote the formula like this, what I said, 2x plus 6 into plus 1 plus minus 2 equal to 0. So x came out to be plus 2. X come out to be minus 2. So are you able to understand? This minus 2 is a average oxidation state because there are two carbon atoms. One is in minus 3, another is in minus 1. So 2 carbon atom has a total oxidation state of minus 4. So one carbon atom on an average would have oxidation state of minus 2. So this is very, very important, which I wrote it here, that the element for which you wanting to find out the oxidation state, if its atoms in the given molecule is more than 1, then with the formula it would be always average oxidation state. And if you want to see the actual oxidation state, then you have to go with the formula. Now let me do one problem for you based on this particular entity only. What is the IUPAC name of a isomer of this in which all the carbon atoms are in same oxidation state? Same oxidation state. Just few minutes back we wrote this formula. This is ethanol. In the case of ethanol, what you have identified, this carbon is in minus 3 oxidation state and this carbon is in minus 1 oxidation state, and average oxidation state of both the carbon happens to come out to be minus 2. But someone else can draw this structure like this also. Wow, beautiful. We may draw the structure like this also. And for this particular understanding, do follow the organic series where I am placing the videos slowly and steadily, and you can refer to that. So here, if you would see the bonding aspect, so here the carbon is, these are the electrons of the carbon, and this are the electrons of the other atoms around it. So if you would see that in this case, this hydrogen would definitely be carrying +1 oxidation state, and this is -1. This also is +1, this is -1, this is -1, this is +1. But from this particular bond, if you could see carefully, because this bond would have carbon in +1, this is in -1. And the same story is on this side because it is chemically identical bonding. So the carbon which I am getting here has a oxidation state. Just let me mark it. So minus, there are -1, -1. So this is -2, -1, -3 and +1. So total would become -2. So this is in -2 oxidation state and this is -2 oxidation state. The fellow is asking, now these two isomer, now this is the beauty of the thing. Although average oxidation state for both the carbons in these two compounds happens to be -2. But if I dig deep into the structure or isomers, all the carbons may or may not have same oxidation state. So here it is in -3 and -1, but in this case it is exactly the same as average oxidation state, and they are asking that isomer in which all the carbons are in same oxidation state. So it is which compound? CH3OCH3. So the longest carbon chain is of one carbon. One carbon means the alk is meth, and this meth did not have any double or triple bond, so it is ane. And what is this? This is methoxy. Methoxy. Methoxy is a prefix for the ether. So we will be saying the IUPAC name is methoxymethane would have, and this particular compound had been ethanol. So this is very, very important to understand here. Now coming on to the next part, let me place some more questions on into. Now C3H4. Now C3H4 again would have different isomeric forms. Let me say that I have you are being provided with this particular entity. Now this is very, very interesting, because if I go with the formula C3H4, so what exactly do I get? If I want to find the oxidation state of this carbon, 3x plus 4 into +1, because hydrogen is less electronegative than carbon, this happens to be equal to 0. So the x comes out to be -4/3. So this is the oxidation state which we get in this particular formula. This may have different isomeric form. Let me take one isomer, that is what you call it as propyne, and see into the oxidation state. So from here, this is +1, this is -1, -1, +1, and from here also -1, +1, and from this particular bond 0, 0. So this carbon happens to have -3 oxidation state. Coming on to this one, so from here it is +1, this is -1, and from here it is 0, 0. So this means this carbon is in the oxidation state -1. Is it okay? Am I making sense? Yes, it is perfectly right. So moving further, okay, I wrote the formula wrong. Just C3H4 it had been. So I should have drawn it like this. Sorry. I just have overlooked it. This is, sorry, C3H4. So C3H4 would have a structure of this type. So from here, what we are able to see here is that this particular carbon now would have, because triple bonded to the carbon, so it would have 0 oxidation state, and here it is +1 and -1, and from here it is 0, 0. So this is in -1. So there are 3 carbon atoms for which the total oxidation state is -4, -3 and -1. So for per carbon atom, it would have -4/3. So this what I was referring here is when the oxidation state of element for which you are finding out and the atoms are more than one, then with the formula it is always average oxidation state. And similarly, if I would go for this particular anion, which we call it as tetrathionate, this is a very important one, tetrathionate. And if I write 4x, if I want to find out the oxidation state of sulfur, equal to -4. So this 4x, so this becomes 12, -12, and this would become -12, sorry, this is 2 minus, sorry, here it is 2 minus. So this happens to come out to be, let me write it once again for you, -2, 6, 2 minus, -2. So this comes out to be equal to 10, x is equal to plus 5 by 2 or plus 2.5. So there are sulfur atoms, 4 sulfur atoms. Average oxidation state for them comes out to be plus 5 by 2. Now how could we see into it, that how does it look like? So sulfur, now this would come with the practice, for which you have a strength in the chemical bonding chapter. So this is oxygen here. So you have to place how many oxygen? These are the oxygen atoms. Now both sides it is almost identical. So this from here it is 0, from here because they are attached to the sulfur. So the oxidation state of this is sulfur. And now from here it is 0. In this particular bond it is 0 oxidation state on both the sulfur because they are of the same nature. So from here it is +2, -2 because oxygen is more electronegative. Here also +2, -2. And in single bond this is +1, this is -1. So the oxidation state for this comes out to be +5. For this is 0 and for this is +5. So in 4 sulfur atoms are having +5, 0, 0, +5. So average oxidation state happens to come out to be +5 by 2. Now this is also a very important carbon suboxide, very popular example, carbon suboxide. In the case of carbon suboxide, the 3x plus 2 into -2 equal to 0. So x comes out to be 4 by 3, plus 4 by 3. Now how does it look like? The molecular arrangement or the structure is like this. One of the isomer of this formula has this structure. So from here it is -2, this is +2. From this side it is 0, 0 because it is attached to the carbon only, 0, 0. Here it is +2, -2. So this carbon is having +2, this is having 0, this is having +2, this is having 0. And this, if I just would mark the oxidation state of carbon. So in totality is +4. For 3 carbon atoms it is +4. So average oxidation state would be +4 by 3. So this way you need to identify all these. Now another, if I would take, these are again a very interesting examples. So this is 4x plus 7 into -2 equal to -2. So this happens to 14 minus 12. So x comes out to be +3. So now for they may ask you like this, that in this particular anion the average oxidation state is +3. Identify is all the boron atoms are having same oxidation state or not. So for that you have to make the structure of this particular species. So the structure for this particular structure, you can refer to the video which I made for the borates or boron family. There are many videos I have done for this, so you can go through that. So in this particular structure, if I would draw this particular structure of this anion, what I am able to see here is that around boron, this is +1, -1, +1, -1, +1, -1. So around every boron, the oxidation state happens to come out to be +3 only. So here, all the borons are in same oxidation state. So similarly, you can try this one also. Here also, this is again a very interesting anion. And now, last but not the least, 2-3 more examples, then we will wind up. So chromium pentoxide. Now if I would go with the formula, x plus 5 into minus 2 equal to 0. So x comes out to be plus 10. Now this is a wrong, because if you go with the formula this way, the oxidation state cannot, at maximum it can go to plus 8, just like in osmium tetroxide. Osmium tetroxide is this molecule. Here the oxidation state of osmium happens to reach to plus 8, because from here plus 2 minus 2 plus 2 minus 2 plus 2, because osmium is a metal and oxygen is a non-metal which is more electronegative. So what I am trying to say is maximum oxidation state for any element you would see is plus 8. It would never ever would go behind or more than plus 8. So this oxidation state is wrong. So to identify what is the oxidation state of this chromium pentoxide, you need to go into again the bonding aspect. So the bonding aspect of this particular molecule is this way. This is the actual bonding of this particular compound, which we call it as chromium pentoxide, and this also is popularly known as to have butterfly structure. Very popular, and many of the teachers of your coaching have taught you. So in this particular case, if I would draw the electrons, because chromium has 6 valence electron, so if you would see into all these arrangement, here what you are able to see, this is bonded to oxygen itself. Here also it is bonded to oxygen itself. These cross electrons are of oxygen. Now you need to be little vigilant while finding the oxidation state. So from here plus 2 minus 2, from here plus 1 minus 1, plus 1 minus 1, and plus 1 minus 1, plus 1 and minus 1. So you are able to see the chromium's oxidation state happens to come out to be plus 5. Now why is it happened this way? Simply because of the fact that this particular oxygen, if I would find its oxidation state from this side, is 0, 0. So in totality, here you have a proxy linkage. This particular oxygen, if I would mark, this is in minus 1 oxidation state. This also is in minus 1. This also is in minus 1. This is plus 6, sorry. I just wrote it wrongly. Plus 1, plus 1, plus 1, plus 1, plus 4, and plus 2 is of that. So this is in minus 1. This also is in minus 1 oxidation state. And this oxygen, which I wrote it here, is in minus 2 oxidation state. So algebraic sum happens to come out to be plus 6 equal to the minus 6. So if I would write it more effectively, or more, this should be written like this. Oxygen, and it should be mentioned it like this. What is being depicted here? That this chromium is in plus 6 oxidation state, and this oxygen, these 4 oxygen are in minus 1 oxidation state, because these are having a proxy linkage, and this is in minus 2. So in totality, the algebraic sum would come out to be 0 itself. Similarly, if I would go for this particular molecule, which we call it as bleaching powder, this also is or calcium hypochlorite, bleaching powder, this is also very interesting. So if I would break it, some offbeat questions I will bring in next practice session also. This is this particular species. Now here, on breaking this bleaching powder, sorry, I just have overlooked it again. So you have OCl negative and Cl negative. It get broken it like this. Now the fact is, the oxidation state which I now would get here is plus 2. This is minus 2. Is it okay? And if it is plus 2, this is minus 2. They already has become 0. So what is the oxidation state of chlorine, which is a confusion to a child? So bleaching powder is an ionic compound which breaks it like this. So now this is hypochlorite ion. Hypochlorite ion. Here you have to be little vigilant about, because oxygen is more electronegative. So from here it is minus 1, this is plus 1. So this oxygen, on one side you have apparent charge minus 1 and actual charge is minus 1. So total oxidation state comes out to be minus 2, and for chlorine it is plus 1. So there are 2 chlorine atom. One chlorine is carrying plus 1 oxidation state, another in the chloride form is carrying -1 oxidation state. As a matter of fact, it should have also been written like this. This is a better way to explain it. So this is in +2, this is -2, this is +1, this is -1. And as a matter of fact, always do remember, actually bleaching powder is a equimolar mixture of calcium hypochlorite and calcium chloride. And what we are writing here is, this becomes calcium, this is a equimolar mixture of these two. So calcium are 2, so I just have taken 1 calcium. There are 2 hypochlorite, so I just have taken 1 and 1 chlorite. So as a totality, this actually which we are writing is an empirical formula. Actually bleaching powder is a mixture of these two together taken in a equal quantity, as a matter of fact. So just added one thing into your knowledge bank. Now coming on to this also is again, this is fool's gold, or iron pyrite is the ore name. This again is a confusing for a child. Generally people do it like this, Fe, and they break it like this, sulfur in -2 oxidation state, and then they start asking me, this is in +4 oxidation state. No, iron predominantly would either be in +2 and +3 oxidation state majorly. In some of the coordination compound it may also exist in +1, but majorly you either would have +2 or +3 oxidation state. So this is a wrong viewpoint. Actually it get broken like this, just like peroxide. This is called as persulfide bond. Persulfide bond, it get broken at like this, just like the peroxides. So sulfur, this is negative, this is negative. So for this particular sulfur, the oxidation state is 0, 0. So the apparent charge which we receive is 0, actual charge is -1. So it is -1, this also is -1. So both the sulfurs are in -1 oxidation state. So if I would write now, this is -1 and this is +2. So algebraic sum happens to come out to be 0. Hope you have understood well that how oxidation state is actually being depicted from the bonding aspect. Is it okay? In the next session, I shall be placing what is the need of understanding this, why we have learned these oxidation state, just to identify what help do we get from the oxidation state or oxidation number, is to identify where would oxidation and reduction are taking place. So this particular thing is well explained in the topic of N factor and the applications of oxidation state. This I will be taking one more session to explain the application part where many things would relate to the oxidation state. Thanks a lot. Have a nice day. Stay safe and take good care of yourself.